Good evening, and welcome to Innovating the Future, the intersection of AI and science. My name is Ann Stevenson, and I'm honored to be here representing Duke Alumni Lifelong Learning alongside my fellow hosts, Duke Triangle alumni and Harvard Club of the Research Triangle. We are thrilled to have you join us for what promises to be an enlightening and thought-provoking evening. Tonight, we explore the groundbreaking integration of artificial intelligence and science. A field is reshaping industries, revolutionizing research, and opening doors to new possibilities in healthcare, drug development, and DNA sequencing. This program is part of our commitment to fostering lifelong learning and intellectual curiosity, bringing together experts and thought leaders to share their insights and spark meaningful discussions. We are delighted to welcome two distinguished speakers who have made significant contributions to the fields of AI and biomedical sciences. First, we have Dr. Akshay Bareja, an assistant professor of medicine at Duke School of Medicine, who is at the forefront of using machine learning and multi-omics approaches to drive biological discoveries. Our second speaker is Mark Shapiro, an esteemed Duke MBA graduate and AI entrepreneur, currently serving as the Chief Operating Officer at XCures, where he is leading innovative applications of AI in healthcare and clinical research. Throughout the evening, we'll dive into topics such as deep learning, neural networks, AI's impact on scientific advancements, and the entrepreneurial landscape in this transformative field. We encourage you to engage, ask questions, and connect with one another as we navigate these fascinating discussions. Once again, thank you for being here and for your enthusiasm in exploring the future of AI and science. Now let's begin with our first speaker, Dr. Akshay Bareja.
Thank you, everyone, for being here on this beautiful evening. Before I begin, I want to thank Anne and the whole Duke team for organizing this. This is such a nice venue. And I also want to especially thank Navneeta Rao, who's a member of the Harvard Alumni Association, and unfortunately he can't be here tonight. He approached me about a year ago with this idea of maybe giving a talk on the intersection of biology and AI, or engaging in some kind of panel discussion. So I'm a biologist with an interest in machine learning and AI, and I foolishly said, sure, sounds like a good idea. And many months later, it blossomed into this. All right, so today I would like to, before I get to this, this talk the alternative title could have been AI from the perspective of a biologist. Now you might be asking yourselves, why would I want to learn about this complicated thing from a biologist? Wouldn't I rather learn about this from a computer scientist or a statistician? The short answer is yes, you should. If you really want to understand these things, you should learn about these things from a computer scientist or a mathematician or a statistician. But the slightly longer answer is I found these things fascinating, and I've spent a lot of time trying to develop an intuitive understanding of how these things work. And I hope that I can share that intuitive, geometric, visual understanding of at least how these simple neural networks work. So today I'll be introducing what I call the world's simplest neural network. This is a stupidly simple neural network that does a stupidly simple task. But I hope that by seeing how it does what it does, we'll all have a better sense of how these larger, more interesting neural networks work. I'll then briefly talk about this amazing concept of word vectors. Word vectors are kind of the fuel of these large language models like ChatGPT. And I'll end with a very high-level description of what I think is a nice use of neural networks in healthcare research. This is a model called DeepDTA. I will not get too much into the details of any of these more complex models, but I'm just going to touch on this as an example of what I think is a really good use of deep learning in biology. All right, so let's begin with the machine learning life cycle and try to just quickly go over some essential vocabulary. So I mentioned deep learning, I said machine learning, I said neural networks, I said a lot of things. I like to think of it broadly as deep learning is a subset of machine learning, which is a subset of AI. So deep learning refers to models that are based on a neural network architecture. What's a neural network? We'll find out soon. Machine learning is a much broader field that consists of many, many different approaches, one of which, approaches and architectures, one of which is neural network based. What is machine learning? We'll find out in a couple of slides. And machine learning sort of sits in this big circle of AI. What is AI? At best, it's a nonsensical term that doesn't really mean anything. And at worst, it's misleading. But there isn't really a better alternative, so we're all stuck with the term AI. Just as a minor aside, I don't want to get into a rant. There's the computer scientist Timnit Gebru, who makes the interesting point that AI is misleading in two ways. One, it's not artificial, because the term artificial intelligence sort of implies that this thing just arose de novo. All of these models, like ChatGPT, stuff that you've worked with, has been built on the backs of many, many real humans, many of whom have been poorly compensated and come from the global south. So I will not get into this thing, but I think there are a lot of important discussions on this. And as you'll hopefully see, these things aren't really intelligent in the way you and I are. At least I hope you don't think so. So what is machine learning? I like to think of machine learning as something that is contrasted to what I'm going to call the programming approach. So imagine we have an image of a cat, right? And we want to build a model that can look at that image and say, this is a cat or this is not a cat. The kind of programming approach might be, okay, I'm going to handcraft a bunch of rules. Like if this image has two pointy ears, has a tail, is fluffy, looks cute, I'm going to call it a cat. The problem with this kind of approach is you can imagine an infinite variety of breeds of cats, pictures of cats, poses of cats. You and I can instantly look at a cat, whether it's sleeping or looking at you or running, and say that's a cat. But if you have these kind of naive rules, it's very easy to violate them. And what is clearly a cat will be called a not cat if you use this programming approach. It doesn't really work very well for something like image analysis. The machine learning approach, on the other hand, is you don't define any rules. You use a particular kind of architecture. So I'm putting the model in a black box, and that might be a term you've heard of before, because a lot of these things are so big and inscrutable, but they still work really well. So you have a model, and you supply that model with thousands or millions of images of cats and not cats. And importantly, you tell the model what is a cat and what is not a cat, and it automatically learns the rules. What are these rules? These rules might not be apparent or obvious, and you might not even care about what the rules are that it's developed. But these things end up working really well, especially for tasks like computer vision. All right, so this is an oversimplified image of a very, very small neural network. So a neural network is made up of what are known as neurons. For the purposes of today's talk, when I say the word neuron, just think number. It's nothing more complicated than that. And neural networks are typically made up of arrangements of these neurons in series of what are known as layers, right? And so in this case, we have 3 layers. We have our input layer made up of 2 blue neurons. We have our middle layer or hidden layer made up of 2 red neurons. And then we have our output layer, which is just this sort of gray neuron. And there are also arrows that are connecting these neurons. And these arrows are known as weighted connections. What's a weighted connection? We'll take a look at that detail in a second. So essentially, information gets put in from left to right, gets processed by this neural network as it moves to the right, and then you have an output prediction. To make this somewhat more real, imagine that the 2 blue neurons correspond to, I don't know, resting heart rate and body temperature. That information gets passed through the neural network, and the gray neuron could be a probability that corresponds to you're sick or you're healthy. And so we have our input, we have our hidden, and then we have our output. So I'll be talking about this concept of learning. Like that's the really important part in machine learning. And the way learning works is you supply your model, in this case a neural network, with an input. It processes that input, and we'll get into the details of what processing means, and it'll make a prediction. And you compare that prediction with the real answer. In this case, are you sick or are you healthy? And based on how badly or well your model made its prediction, updates will be made to these weighted connections in such a way as to improve the model. That was just like a couple of sentences, and there's a lot in those couple of sentences. But essentially, this is the entire machine learning lifecycle as it applies to this simple neural network. Yes? Great point. Okay, the question was, how does the machine know whether it made a good prediction or a bad prediction? I will bookmark that question because I'll reveal the answer in a second. But that's really important. It's important to know how do you give it information? How do you let it know how well or badly it's doing? All right, before we get to that, I just wanted to give a super brief mini early history of neural networks, primarily to illustrate the point that a lot of the ideas that are being used now and that have led to this modern AI renaissance were actually proposed about 100 years ago, which is pretty amazing. So this is a biological neuron, and just a very oversimplified view of how it works is it contains these mini projections known as dendrites, and these dendrites are ways in which the neuron can retrieve electrochemical signals or receive electrochemical signals from neighboring neurons. So it receives those signals, and within the body of the neuron, it assembles those signals and sums them up. And if that sum crosses a particular threshold, neuron then fires its own signal down this axon, the length of this long projection, to the next neuron. And this idea of the oversimplified view of how the biological neuron worked inspired these two people, amongst others, Warren McCulloch and Walter Pitts, to publish this landmark paper, which has a very catchy title, A Logical Calculus of the Ideas Immanent in Nervous Activity. I can never remember the title. In 1943, what they did is they came up with a mathematical framework of how neurons work. And so they introduced the concept of the artificial neuron. They were the very first people to do that, to publish it. And they showed in their paper that if you arrange these artificial neurons in different arrangements, you can perform various logical operations. And this man here, Frank Rosenblatt, was deeply inspired by this paper. And so he generated the world's first physical artificial neuron. It was actually one of the world's first physical machine learning systems. And he called it the perceptron. And the idea is behind this artificial neuron is it's very similar to the oversimplified view of a biological neuron. This artificial neuron takes in one or more inputs, sums them up, and then decides to send a signal or not based on whether a certain threshold is crossed. And Frank Rosenblatt's perceptron actually was used to do some really revolutionary things at the time. He built one of these perceptrons, the Mark I perceptron, was able to look at two images and discriminate between them. So it could look at an image of the letter A and the letter E and say whether it was A or E. This is amazing. People lost their minds over this. It was a ChatGPT moment in 1950-something. But unfortunately, that didn't last very long. And one of the reasons was this perceptron, as he had defined it, could only perform very simple tasks. And there's this long history of AI of alternating winters and summers, and apparently we're in a summer. And so this was the first AI summer, which was followed by an extended AI winter and then another summer and so on. But his idea of a perceptron, the neural network that I will show today, the very, very simple one, is remarkably similar to the idea that he proposed. and Warren McCulloch and Walter Pitts proposed. All right, so let's build this super simple machine learning model. Actually, we're going to do 2 neural networks. So this is the problem that we're trying to solve. I promise there will be very few equations and not that much maths, but and not that many axes, but and everything will be in 2 dimensions because I can visualize in 3 dimensions, but it's easy to do things in 2. So the way we're setting up this problem is we're trying to predict something. And what we're trying to predict is the color of a circle. Is the circle red or is it blue or purple, whatever that is? And the inputs to our model are 2 values, x1 on the x-axis and x2 on the y-axis. And the idea is if our input is 0 and 0, we want the model to predict red. If it's 1 and 0, we also want the model to predict red. If it's 0 and 1, we want to predict blue. And if it's 1 and 1, we want to predict blue. So naively, one idea we can come up with for our model to learn is this very simple rule. I'm going to call anything that is above this line blue and anything below it red. Now, this is a stupidly simple task. Like, we don't need to build a neural network to do it, but let's just do it for fun. We don't really have a sense of telling the neural network what is blue and what is red. Because one thing about, at least the neural networks I will show, they take in numbers and they produce numbers. So instead of saying blue and red, we're going to code red as 0 and blue as 1. So another way of framing this problem, the 3rd column should say y on the top, is like this. If it's 0 and 0 as input, we want 0 as the output. If it's 0 and 1 as the input, we want 1 as the output, and so on. Okay? So the particular neural network we'll use is a very simple one. It's arguably the simplest one I can think of. We have 2 inputs, those 2 blue neurons that correspond to x1 and x2. Something happens, which I'll go over in a second, and it has an output. Now, the something that happens is this processing with these weighted connections that I mentioned a few minutes ago. So the weighted connections here, W1 and W2, so what happens is you take your first input, x1, and you multiply it by the first weight, W1. Then you take your second input, x2, and you multiply it by W2. So you have x1, W1, x2, W2. And you just add them up. And then you also add, you can see it floating up there as this B, that stands for bias. You also add that term to get this computed, this Z term. And then you do one more thing. You pass that Z value through this function known as a sigmoid function, which, if this is your first time seeing it, might be a little bit scary, but it's a very simple function. It takes in any continuous value from -infinity to +infinity, and it squishes it to be between 0 and 1, which is a reasonable thing to do in our case because we're trying to predict 0 or 1. And so then we get our model's prediction, which we can call y hat. And we do one more thing. If y hat is above 0.5, we're going to call the thing 1. That's our model's prediction. And if it's less than 0.5, we're going to say our model's prediction is 0. So these are all the things we've done to set up our neural network. This is just as an aside. An alternative way of visualizing that drawing there is as this is like a function here. Y hat is equal to sigmoid, and then x1 times w1, and so on. And this is just here to illustrate the point that these neural networks, you can think of them as functions. Just like a function takes in an input and produces an output, a neural network does the same. In fact, there's a lot to be said about how these neural networks can approximate any continuous function, which is pretty amazing. Okay, so how does our model learn? We've set up our architecture, we've set up our strategy, we have our training data, but how do we actually learn? So I mentioned these weights, W1, W2, and a bias term. We start off by just randomly initializing them. We just give them random values because we don't have a better choice. You then start supplying or inserting your input data into this untrained neural network, and it'll start to make predictions. And as you can imagine, these predictions are going to be pretty terrible because it doesn't know anything. You then compare those predictions with the actual answers, which are also known as the labels. And So this is to the questioner's point. You have this very important function known as a loss function. And the loss function's job is to compare the prediction of the model with the actual answer. And it produces a certain value. And typically, that value is high if your model has made a bad prediction, and it's low if the model's made a good prediction. And that value is used to make tiny adjustments to the parameters of your model. What are parameters? It's a collective term for the weights and bias terms. That one sentence there, just given the amount of time I have, is actually doing a lot of heavy lifting. This make tiny adjustments to the parameters to decrease this loss. This strategy was described in this paper. It's this thing known as backpropagation. It was introduced in 1986. And one of the authors of that paper, Geoffrey Hinton, won a Nobel Prize recently. But the surprising thing about that, and maybe we can briefly talk about it later on if we have some time, is that very brilliant procedure makes use of high school level calculus. And I just threw this in here. So I mentioned loss function. The particular loss function I used in this example is this thing called binary cross entropy. I'm not even really sure why I put that up there. It's not really important for you to remember that, but just in case. All right, so there's a lot going on in this picture. But what this picture shows you is the performance of the untrained model, right? So we have our original 2 blue circles, 2 red circles. But then we have the sea of red and sea of blue. What does this mean? So what I did was I sampled every pixel, well, not every, but many, many, many pixels in this graph. And you can, in each pixel, each point in this graph can be defined by an x1 value and an x2 value. And I just put those numbers into the neural network, the untrained neural network, and it predicted red or blue. So that sea, you can see that sea of red predictions and a smaller lake of blue predictions. And what you see is you naturally have a straight line that divides the red from the blue, and that's known formally as a decision boundary. And the way to read this is, if our model put the blue circles in the blue sea and the red circles in the red sea, it did a good job. If it didn't, it did a bad job. And in this case, you see 2 blue circles in the red area, 1 red circle in the blue area, and 1 that it just happened to get right. So it's 75% inaccurate. It's terrible. So what do? We go through the learning process iteratively. This is a new term, epoch. An epoch refers to when you supply your model, when you show it all the available training data. And there's nothing to stop you from doing that over and over again. And that's typically done in any kind of training process. So an epoch of 10 means we've shown our model, our training data 10 times. And this is how it's done. Still not so good. We do 100 epochs, still not so good. Finally, after 1,000 epochs, it's done pretty much what we want it to do. It's calling the blue circles blue and the red circles red. Okay, so good job. Let's look at a second example of the day. Now, this looks a lot like our original problem, except instead of having 2 blue circles on the top and 2 red at the bottom, we've switched one of them. Now, the right red one is at the top and the blue red one's at the bottom. Okay, let's see how our model does. So once again, we train our model with this training data. So we can see the 2 inputs and 1 output. And since our model previously, without changing its architecture, was able to solve our first problem after 1,000 epochs, let's see how it does after 1,000 epochs here. It's no good. Maybe it's just a case of like, we just need to show it the same data over and over again. 10,000 times, still no good. 100,000 times, still no good. 1 million, there's no point. Hopefully by now you can see that this model is only capable of drawing straight lines, decision boundaries. And there's no way to separate the red from the blue with a straight line. We need something a little bit more complicated. This is the added complexity. Now, this is also known as a multi-layer perceptron, I guess in honor of Frank Rosenblatt, or a fully connected neural network. And it's fully connected because we've added really just one more thing. We've added this. So our original neural network had an input layer and an output layer. Now we have an added hidden layer marked by H1 and H2. And that hidden layer is doing a lot of what I'm going to say is magic. It's not really magic, but it's amazing. And now we see these arrows. There are more arrows because there are more neurons. And the idea is each neuron in a inner layer is connected to all the neurons in the next layer. But otherwise, everything else stays the same. We're multiplying by weights, we're adding them up, and we're applying the sigmoid function that squishes everything from 0 to 1. We've just added these two new neurons, H1 and H2. Everything else stays the same. Let's see how this neural network does. Beautiful job. Because it's now able to draw this complex decision boundary. And if you ever wonder why people, GPT-2, when it went to GPT-3, they went from, so many million neurons to 10 times more neurons. Like, why? What's the point? Why are they adding this? Hopefully, this shows you that there's a good reason, or there can be a good reason to adding more neurons, adding more layers. Okay, it did better. I mean, it did a perfect job, but it's not immediately obvious why adding 2 additional neurons, introducing this hidden layer, makes things suddenly, better. I want you to now sort of forget everything about weighted connections and the actual computations. They're not that important. I want you to sort of, when you look at this, break it into 2 parts. This first part, that's performing transformations to your input data. And these transformations the goal of these transformations is to produce a better representation of your input data. And then the second part is just a linear classifier, right? Something that can just draw a straight line. So what do I mean? And then this hidden layer is also known as a latent representation. So we have our original space. When we undergo these transformations, this is what is happening in the hidden space. All those multiplications with weights and addition of biases and adding those sigmoid functions, they have had the effect of moving the red circles to the top left and the blue circles to the diagonal. And what's amazing is these are plots that correspond to a real neural network that I built and trained. So I didn't decide to put the red circles up there and the blue circles here. And now your final part of the neural network, which is a simple linear classifier, now it can easily draw a straight line that divides the red from the blue. And that's essentially, I don't want to oversimplify things. At the risk of oversimplifying things, that's essentially all that's going on. And when you think of something like ChatGPT isn't merely made up of many multi-layer perceptrons or fully connected layers, but it has many it's built up of many modular units that don't look that dissimilar from this thing. There are, of course, many innovations that have been introduced since 1943 that have made ChatGPT what it is, but a large part of it looks kind of like this stupidly simple neural network that I've shown you. Now, if you're anything like me, static images are fine, but animations are so much more useful. All right, so we have our red circle, our blue circle, our red circle. We pass it through the neural network, and that's what it's doing to this space. That's what the weight multiplications are. We add our bias terms. We apply our nonlinear sigmoid function. Now we have the reds to the red, blues to the blue. We can draw a straight line. So this is a much more intimidating, more complicated neural network. It's called a convolutional neural network. And it was designed to be able to do computer vision tasks. So in this specific case, this neural network can look at hand-drawn digits from 1 to 9 and accurately classify them. While this might look on the surface completely unlike the simple neural network we just took a look at, it is, broadly speaking, composed of the same kinds of operations. It's made up of many neurons. We have all these weighted connections, and we have all these nonlinear functions. It's just a sequence of them. When you see something like this, once again, think what's going on in all these earlier layers of transformations to transform our initial input, which is this 2x2 image of pixels, into a more useful numeric hidden representation. that you can then easily do linear classification on. And as non-compulsory homework, I recommend this wonderful tool. Many of you probably already know about it. It's called TensorFlow Playground. And you can run neural networks in your browser. And you can see that this also allows you to train neural networks to do extremely stupid things like this sort of thing we just did. Can you tell a yellow circle from a blue circle? But they look a little bit more complicated than the example I showed. This one is in my opinion, the most interesting example because it's been the most edifying for me to build a neural network that can solve this problem and then understand why it was able to solve that problem. So here you're trying to draw a decision boundary to separate your blue circles from your yellow circles, and then you can play around with neurons. You can add neurons, you can add layers, you can mess around with anything. You don't need any code to build and train a neural network. And here's a challenge. Try to build the smallest possible neural network, given this, that can accurately solve this problem. And then, homework part 2, I recommend this paper with this intimidating title, Neural Networks, Manifolds, and Topology. And it's by this person, Chris Olah, who I believe now works at Anthropic. He's a brilliant machine learning engineer, but he's, I believe, an even more brilliant educator. And he goes through a much nicer, more sophisticated version of what I just showed you, a geometric visual depiction of what these neural networks are doing. And he actually considers this example of the circle within a circle. And it's really beautiful how he shows you what's going on in that magical hidden layer that allows the neural network to be able to accurately classify blue and yellow. All right, so very quickly, in the last few minutes, I'm going to introduce this concept of embeddings, which again, doing zero justice to this very complicated topic. But so I mentioned this term or this concept of useful numerical representations. So continuing that theme, I also mentioned the neural networks. They need you to supply your input in the form of numbers. In our very simple case, x1, x2, they were already numbers. We didn't have to do any work. In the case of images, images are also numbers. They're pixel values. You don't have to do much work. But words aren't numbers. That might be the stupidest thing I've ever said. So we have to do something. We have to convert these words to numbers. So one way of doing that is to come up with, let's think of a barcode representation of a word. And by a barcode, I mean a sequence of numbers that define something about that word's meaning. I know New York's not a word, but let's pretend it is. So let's imagine we have these 3 words, New York, Chicago, and Bangalore. Those are the accompanying, let's say, barcodes. And if these sequences of numbers, which are known as word embeddings, if they have been learned or designed in any kind of useful way, it would be reasonable to expect that the word embeddings for 2 words that are similar to each other are similar to each other. And words that are different have completely different word embeddings. So that sort of heat map there sort of shows you that big picture New York, Chicago, and Bangalore you'd expect them to have similar word embeddings because they're all cities, they have lots of people, and so on. But if you put the word banana, you'd expect it to have a completely different word embedding because it's a fruit, and cities aren't fruits. So this is a reasonable idea, but imagine if you had to handcraft these word embeddings. It'd be impossible. Too many words, and you'd have to do it in a way that everyone else agreed with. So, thankfully, there was a group at Google who about 10 years ago came up with this algorithm called Word2Vec. And Word2Vec is based on a very, very simple but powerful idea. You know a word by the company it keeps. What does that mean? Let's say you're an alien and you know nothing about words, but you just look at the neighboring words for a given word. What you will find is words that tend to have similar meaning tend to have similar neighbors. Like the cute dog ran across the floor. The cute cat ran across the floor. Look at my pet dog. Look at my pet cat. But you wouldn't say, look at my pet floor, right? And so they exploited that very simple idea, which is actually a decades-old idea. And they came up with this strategy. Actually, they came up with two different strategies. One is take huge amounts of text, break them down into small sequences of 5 consecutive words. Pick the middle word, and then use its 2 or 4 neighbors, 2 on each side. Compute embeddings for them, sum them up, and then using kind of like what we did, I'm not showing the details here, use that sum to predict what the middle word is. So out of the entire vocabulary, you want to pick the word that's actually in the middle. And they did this many, many times to learn these word embeddings, and it ended up being really successful. Now, just in the interest of time, I am not doing this any justice, but I'd strongly recommend that you read this. If you don't know nothing about word2vec or word vectors, here's a wonderful visual article that describes how the word2vec algorithm works and how these word embeddings were learned. I've got 2 minutes. But this is the output of this word2vec algorithm. We have these sequences of numbers, which are, I believe, more easily visualized as barcodes. And what they found was you could do this remarkable vector arithmetic on words. And they were able to solve these kinds of analogy problems. Like they took the word vector for king, subtracted the word vector for man, added the word vector for woman. And what they ended up wasn't the word vector for queen, but one of the nearest vectors in this high dimensional space was the word vector for queen. So it was actually learning it was through these word embeddings that were computed using this very simple strategy, it was sort of able to reconstruct the relationship between words without really having any sense of language, or without being taught explicitly rules of grammar or what's a verb, what's a noun. It just sort of worked it out itself. Now, again, we could go off on a tangent about the sort of darker side of AI, but I'll just put this one slide up here. I'm sure everyone can complete this heading, unfortunately. Man is to computer programmers, woman is to. Turns out it learned homemaker. And there have been various ways since 2016, and also included in this paper, strategies for debiasing these word embeddings, but this continues to be a problem. All right, I'm going to end with a very, very high level, so sort of to bring everything together to something that is deeply relevant to me, biology. There's this wonderful model called DeepDTA, which now I realize 2018 feels like an eternity ago. But the goal of this DeepDTA model was to take a drug and a protein and to be able to predict whether they would bind to each other and how strongly they would bind. Now, interestingly enough, you can depict a protein just like a sentence is a sequence of words. A protein can be represented as a sequence of amino acids. Similarly, a drug can also be represented as a sequence, like carbon, nitrogen, double bond. That's called a Smiles representation. And it might not be immediately, actually, it's not apparent here, but just as we learned word embeddings for words, you can also learn word embeddings for like the M there, which is methionine, or the C, the carbon. And so that way you go from this one-dimensional sequence of Smiles and amino acid sequences to a sort of two-dimensional array of numbers. And so then you can use this convolutional neural network that I briefly mentioned before to sort of treat these inputs kind of like pictures. Anyway, point of all of that is to go from this non-numeric representation to a numeric representation that goes through the neural network. The neural network does all of these this processing and transformations, kind of like what I mentioned a few slides ago, to learn useful representations of your inputs. And then in this particular case, they built 2 towers and then they just concatenated the outputs, but concatenation is just a fancy word for putting them together. And then they passed that through another part of the neural network that actually that bit up there that says FC, 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 that's essentially identical. It's a bigger version of what we just saw until it produces one output, which is the prediction. So all of this is to say there's a lot going on here, and I'm not doing this any justice. Like this would be what you would, I imagine, I hope, be introduced to in like a graduate level course. But essentially what's happening is, and I'm taking some license here, not that dissimilar from what you saw with a very, very simple neural network. With that, I will end my talk. Thank you for your attention, and I'll hand it over to Mark.
All right, that was great. Thank you, Akshay. And thank you to the Fuqua, or I'm sorry, the Duke and the Harvard Alumni Clubs for hosting this. It's really a pleasure to be here. I thought that was a super interesting talk. I'm not going to have as much math, but I'm going to talk about this more from the business perspective, which is how I've been thinking about it for the last several years. It's been a transformative time. And I hope to leave you with that thought that this is actually not an AI winter, not a summer, but really like this is the future, and it's going to be this way. I didn't believe that 6 years ago, but I have come along to believe it now. I'm going to start too with a few disclaimers. I won't read these to you, but just making it clear there's no legal, regulatory, or investment advice here. A little about me. So I'm the chief operating officer of a Series A venture-backed AI company. We do health technology. It's not exactly what we started out to do, as you might imagine, over a 6-year period with a startup. But it is very AI intensive, what we do. I was previously head of operations for a clinical research company. In 2018, after we sold that company to a PE firm, a couple of computer science professors at Stanford hired me to write a business plan. So they had this idea that they would use AI to train a clinical decision support model for oncology. So this would be an AI system that would help doctors decide what to do for patients. This is very different from the earlier iteration of this, which was IBM Watson for oncology, which was training a machine learning model to predict what doctors already knew. This was talking about patients who there was no guideline. And it took us down a really interesting pathway as to what was possible with this technology and how that changed during this period. So our goal was actually FDA approval of this product, which did not happen, and I will talk a little bit about why. It was a really interesting period of time, right? And I think this is what's super exciting. When I started this, AI was sort of a joke, right? Even the top people at Microsoft, right, we'd say, all we're really doing is machine learning, right? And we do machine learning in Python, and if you see AI, it's going to be written on a PowerPoint slide, right? It's slideware. It's not a real thing. And that was pretty consistent belief. Like, we were doing, or in practice, logistic regression, what Akshay showed you, this, let's classify it on a sigmoid curve, right? That's basic logistic regression. That's a lot of what people were calling AI, but that's what was happening. And something really fundamental happened, right? We went from this is a joke to let's all spend $80 billion and our investors are happy with that. So this is real. I think, these are smart people who know how to invest their money and they're putting a lot of it behind this. So what happened? People came up with catchy names for neural networks. This one, they came up with a catchy name called the Transformer. This was a team at Google in 2017. This is not a widely noted paper. I mean, it was one of lots of people publishing papers with neural networks, with new architectures, giving them cool sounding names. It turned out, though, this one was really good at one task, which was sequence generation of words. It would take a few words and give you a good answer for what the next word should be. Obviously, you guys know the story here, right? Google developed this into a great product. All these people made a lot of money. So none of that really happened. These people don't work at Google anymore, but writing this paper helped them all raise money. They all have startups. And Google kind of missed the boat. I do want to point out, I do think this is probably the most transformative scientific article of our lifetime. This is really something that's different. So what happened? These kind of crazy guys at this nonprofit called OpenAI kept working on this, and they kept raising money, building software. And in 2019, they realized, when they were really socially conscious about AI, hey, it actually produces stuff that sounds real. Like this idea of the Turing test, which had been around for years. Could you tell if somebody was human on the other side of a barrier? It seemed to pass that test, right? It generated text that seemed legitimate. And they were thinking about it from the standpoint of, wow, socially, what happens if we release this into the world? That was 2019. They've changed a little bit since then, including not being nonprofit anymore. But they really came up with, I think, two key innovations here that turned this from like a cool thing, a cool idea, to something that consumers could interact with. And those two things were model scaling. So GPT-2 was 1.5 billion parameters, right? We were looking at 2, 4, 6 parameters before. So they scaled it up, right? Something that couldn't have been done before. Microsoft made a great investment. So they changed their minds, right? They put $1 billion. That was a great return. OpenAI decided, let's not be so open about this. And then they started training on all the data on the web. They weren't the first people to do this. Google indexed the whole web. These guys decided, let's take not a bunch of books, but let's take all the data in every language and feed it all there and see what happens. And it turned out it actually could do some cool stuff. You could ask it something and it would give you an answer, right? You didn't have to code the answer. You didn't have to create the rule. And they were pretty excited. I think this is pretty cool. But it wasn't until 2022 when they actually came up with this other idea. Let's train this. Let's just have it generate answers and have humans pick which one's the better one. Do that like 20,000 times. And then suddenly, that fine-tuning makes a chatbot. It actually starts to talk to you, right? I don't know if you guys remember, there's a guy at Google who's like, these things are conscious. But it has a semblance. Like, if you interact with it, it can have a conversation with you. That was called reinforcement learning with human feedback. They've kind of moved on. These things are training themselves now. Humans are more out of the loop than they were. It was also the most successful product launch in history. They had 100 million users in 3 days. So I'm sure the IT and infrastructure team, they were running on Azure, which is Microsoft's cloud, was very happy about this. Google, obviously, not so happy about it. Really interesting time because nobody was putting this stuff in products, right? This is all experimental, but now it's all, or it should be, you should be thinking about this for your business as part of a product. So while they were doing that, we were building AI decision support for cancer. We were thinking about it in what was a state of the art at the time, which was a recommender system. And this you're very familiar with, whether or not you know how they work. Amazon, TikTok, Netflix. Netflix was at one point considered the best of this. Really just, machine learning ensemble models. What is this person like? What do other people like? What are things like that? Let's give them to you. And we thought we would do something like this. And we had some, GloVe, which is similar to Word2Vec, natural language processing, and a lot of Bayesian multi-level machine learning. We thought, okay, we could train a model that could do what an oncologist would do. It would help them. And we did that. It actually turned out to be, in some ways, easier than we thought it would be. We trained on a bunch of clinical trials and publications, and then we fine-tuned with human tumor boards. And, we got pharma interested. They gave us some millions of dollars. They said, we believe that computers are going to help doctors prescribe medicines. We want to be in on that. And, I still think they're right about this. So we took this to the FDA and discovered they were very interested in it. And there was probably no way in their mind legally that they could approve a device that did something like this. And I think that's probably still true today. But you'll see that it actually performs as well as a human molecular tumor board, which is a big accomplishment. This is pre-transformer models now. It shows that there's some tractable problem here. You can model how oncologists think. It also, led us down this path of, well, how do you know how good it is if there's no standard to train it on? And I think this is the type of learning that we're dealing with now with these models, which is, you have red dots and blue dots. Now we don't know what the answer is, but these models can figure out answers in that situation. And that's a really, take that in for a moment. They can figure out solutions without being given the answers. And they do that by transferring knowledge from all this other stuff. So they can make insights. So we took this to the FDA. They liked it. They told us we could keep doing what we're doing as long as we don't claim that it helps patients. You know, nobody can't say it lives longer. We had about 250 oncologists who used it, liked it, treated patients based on its recommendations, but we couldn't sell it. So we ended up in the situation of, do we sell the company or do we keep going? I think we still believed at the time in what we were doing. We decided to keep going. We published a chapter in this book, AI in Clinical Medicine, which is a great text for physicians, covers how AI is being used in pretty much every branch of medicine. Mostly AI is being used in imaging right now. And we ended up deciding to basically sell the software that we use to go gather all the data and process it for the AI. And it turns out lots of people have that same problem. So, you know, today we sell mostly the software back to hospitals, labs, health systems, and they use it to fill in gaps, missing information that they don't know. AI plays a role in this. I asked Akshay to talk about Word2Vec because for us, this is a lot of natural language processing. We want to find information in medical records. Probably the best analogy here is just, we wanted to slap Google search on top of your medical records. And it turns out that's pretty hard to do. And there's a market for it. So, you know, we do add AI now. We have transformer models. We summarize documents. We found recently, like, people want us to summarize faxes for them because hospitals are still faxing each other to the tune of like 20 million a month. And they say, like, somebody's got to look through the fax. We'll just put the fax into the AI and tell you what it says. So, I mean, some really mundane stuff. It's not curing cancer with AI, but, you know, that's not what the healthcare system needs. Like, it's not ready for that yet, I think. So we're still very bullish, and I think, you know, everybody in this room should think about AI in healthcare. Baumol's disease, Baumol was an economist. He was describing healthcare. So Baumol's disease is this idea that, you know, things that can't scale, that can't take technology to increase productivity become more expensive, right? And healthcare, right, you've all heard, right? I don't need to tell you that healthcare is at the top of that list. So healthcare is super attractive to technology companies because they are looking at this as a huge pile of money, huge inefficiency that AI can come in and take a piece of. I would say I firmly believe in that as well. You know, a lot of factors, a lot of tailwinds for why you would want to apply AI here. Basically, you can't force doctors to see patients any faster than they did 50 years ago, right? So we were really thinking about information overload, right? 1.5 million peer-reviewed medical journal articles a year. So how does a doctor stay current? We did this analysis on oncology guidelines. Compound annual growth rate, 10% a year in guidelines, 10% a year in pages. Right? That's a lot of information for a doctor to know to stay current. More acute in the community than in a place like Duke where doctors see one type of cancer or a few related types. But information overload is hard. AI is really good, right? We all use the internet because AI indexes that information for us. So that's where we think, you know, there's real opportunity here. And in this other place, right, 30% of the employees in the healthcare system are administrative, right? So that feels like an opportunity as well. Improving scheduling, billing, coding, charting, right? The biggest, or one of the biggest sources for physician burnout, other than COVID, was EHRs, right? They don't like to be forced into using this computer. So what can we do? Can AI let them practice medicine and take some of that burden away? You know, and what I said is, like, why now, right? This revolution is not just technology now, it's applied. There's massive competition. Like, this used to be very hard. We'd have to custom build a model, have to design a whole neural network from scratch, right? All those boxes for your specific application. This stuff is all off the shelf. There's an API, it's super robust. You know, we're estimating, we make 10,000 calls a minute to the OpenAI API, right? So we're doing this at scale. These things are built for scale. All those companies are competing. They're spending, $300 billion this year in CapEx, right? So they've got to expect a huge return on that. And the advantage though is prices just keep coming down, right? So this is the time to think about applying it in your business. I also think one of the interesting things here is as interest rates came up, it thinned the crowd. Like there was a lot of hype in here. I think that now the people who are left are really doing stuff, so there's more legit companies in the space. And it's a ripe time. I also like this cartoon up here behind me. I think that's really like when we're dealing with these neural networks, it sort of looks like this, stirring a bunch of matrix multiplication till the answer looks right. This is really, I think, one of the key points I want you to take away too is, right, Moore's law is this idea that computer chips gained like 10 times as many transformers, one order of magnitude every decade, right? And we've lived through this now for 50, 60 years. Right now, AI is scaling at 1 to 2 orders of magnitude a year, right? So we've never lived through a time like this. Like there's never been a time in human history where technology was moving that fast. And it's hard to predict. Nobody has a baseline to predict what that means, but the people who are trying to predict it say, we're on track. And there are people who disagree, but I would say we've exhausted public data, massive amounts of private data, right? Data is a valuable currency right now if you have proprietary data. Architecture scaling, right? If you guys saw the news, DeepSeek, those guys came up with some clever ideas on neural network architecture. Models are getting better. Most of the improvement last year or two, they've been trying to make it cheaper. So, architecture continues to get better. Data centers are growing. This is a very energy intensive business. Inference time scaling is about 4 months old. This was like GPT-o1 and DeepSeek. This is the idea that the model doesn't have to spit the answer out at you immediately. It can think. It can have these processing loops where it thinks, how do I solve this question? Oh, I need to go get this information. Thinking a little more like a human, right? Those models, so lots of ways to get more orders of magnitude here. Hard to predict what it'll be like, but I think I encourage all my employees to use it a lot. It makes them more productive, and I think you should all think about it that way. It can make you and your company more productive. When Mark Zuckerberg was spending $10 billion a year on VR glasses, the market hated Meta. He's spending $60 billion a year on data centers, and they love Meta. Everybody has been giving tons of money to NVIDIA. Those guys are essentially the biggest winners right now in all this AI stuff. But it's worth noting when DeepSeek just published the other week, right? They trained a similar model for $5 million, 1/100th the price. NVIDIA market cap dropped by $500 billion. So there's a lot of money riding on this, but people are fighting to make it more efficient and make it more accessible. I think the big companies would like to hoard it, but there's also a big open source movement here. Hugging Face, one of the companies I mentioned, replicated that 2 days later, open sourced the whole thing. So a lot of opportunity to get into this right now. From a business standpoint too, this I think is really the question. They're spending all this money, they're smart. Where's the return? Like nobody sees the return right now, but they keep spending and the market keeps giving them money to spend. So there's obviously an expectation here that something big is going to come out of this. It could be wrong. We could go back to the AI winter. I hope not. But Goldman Sachs, Sequoia, these are smart people, some of the smartest financial people. And they're trying to do the estimates on what the return needs to be. And it needs to be several X what people are spending. So where is that going to go? And I think if you ask me right now, the competition is making it very accessible for people to use this technology. And it's going to be the people who figure out how to apply it to their problem, right? Meta, IBM, Google, they don't know what your business does, right? So you can apply it right now. You have data, you understand a process, you can make it more efficient with this. And if you think about it that way, there's like tremendous opportunity for people to advance their business right now, or science, or whichever application. I think this makes people more productive across all domains. And it's going to change things. Like we are going to be automating more and more of the workforce. I think this will have real societal consequences. potential for disruption in employment, potential reshoring, like call centers in India or the Philippines could be done by chatbots now, right? There's going to be this shift of jobs that were offshored disappearing altogether. There's going to be one guy who does care and feeding on that AI model that runs that thing. But it's going to really change things. When I started doing this, I thought Jim Keller's quote, he was the head of AI at Tesla for 9 years, not there anymore. But he said, that progress disappoints in the short run and it surprises in the long run. And to me, that's really been the story here is like day to day, you're working on this stuff, it's hard. But then if you look back 2-3 years, like, wow, this has been transformative. I think it'll continue being transformative in a way that, people have been talking about agents, this idea that the AI could actually do somebody's job. That stuff is coming. Right. And it's not going to replace all jobs right away. But you got to think about like, where do you have highly automated knowledge tasks, right? Where could you create the assembly line of the paper world, right? People shuffling SOPs, right? That stuff can happen, right? The technology is there. So, with that, I'd just like to thank everybody for coming and, happy to take questions.
I have a million questions, but I'm thinking about the 100 million people who initially signed up in 3 days with ChatGPT, and I'm thinking about the 8 billion other people who don't have access to this information, nor do we necessarily have access to the information that they have. So if we're thinking about medicine and things that cause cancer, we're really confined by a pool of people. Let's say the Western countries, and those types of ailments. And so I'm just wondering and curious about research into those other 8 billion people who we don't know what's happening to them with regard to food, safety, security, all of those things, right? Mm-hmm. Because that last point you made about outsourcing jobs, I'm like, well, okay, there are other things that we could help people learn in these countries where we're outsourcing labor. And I think that might be the place that you would want to invest, apart from investing back into the same 100 million people.
I think it's right to think about societal dislocation, right? And this is not unprecedented, like automation and factories and shift from agrarian societies to industrial societies. We need to be prepared for it and think about it, at a national, international, holistic level. So it's a tough problem, but I think we need to think about it largely because those companies that are pursuing this are not thinking. OpenAI's focus has shifted, but this is happening. It's going to happen. There's probably nothing that's going to stop it from happening. And so thinking about it, this is why I encourage you to be on the forefront of this. Some people in the AI space were saying like we should not teach our kids math, teach them to be plumbers and stuff like that. But, AI could be doing, plumbing robots in 10 years, possibly, who knows? It's moving fast. It's hard to predict. Yeah.
Hey, Mark, great talk. Thank you very much. My question is more on the business side of, you talked about a number of use cases that you're pursuing, and throughout your slides, there are a lot of evidence of use cases, business problems to solve. What are some of the attributes of a use case or a business problem that make it ripe for innovation with AI? Because it's not always the solution to every business problem. So what are some of the key things that you and the team look for in order to say, this is the use case that we want to pursue?
It's a good question. I think, we're trying to listen to our customers, right? What do they want? It's really good at finding information, and it can be good at synthesizing and summarizing information. So when you have this information overload, like I think a lot of businesses are sitting on a lot of data, right? They've accumulated a lot of documents and reports and stuff like that maybe a few people know, but if you were to put it into an AI model, suddenly, your employees can ask questions and get an evidence-based answer, right? So it can make people more productive. So this knowledge-based piece, I think, is really useful. I think the more vision, object-oriented stuff is still, a work in progress, right? It's not as good with images yet as text. Yeah.
I got one right here. Here you go.
Get a mic.
Thank you. It's a really informative conversation. So you list a lot of different large language models, some more open source, some more sort of a closed. OpenAI is actually should be called closed AI nowadays.
Yeah.
But from your business, from medical and healthcare, which one is more appropriate and what are your customers looking for?
Yeah. That's a really good question. So there's this proprietary camp and then there's the open source camp. And Meta is really in the open source camp. They firmly believe they look at open source software, right? Open source software has really thrived. Meta and Google open source their software and they create a bunch of people who know how to program their software when they come work for them, right? So the open source movement is really their bet is basically people are going to customize it, right? I can take Llama 3, which is Meta's model. I can run it inside my own servers, train it on my own data. I don't have to tell anybody what it's trained on. OpenAI is taking we have a bulletproof infrastructure that you can call, 10,000 times a minute. We'll give you some lightweight tools to fine tune it, but it's more of a infrastructure as service, really. And, we've gone back and forth, right? We hosted models. We went to high scale production, with cloud service providers. We're now actually bringing some of that stuff back in because we got to the point where we're need to fine tune it a little more for our application, need to have more control over the scaling and the rate limits and stuff like that. So, I think you might find in the application process, it's easy to start somewhere. You scale enough that you're going to need to bring it in-house, but there's a life cycle. And I would say for us, we have lots of models in production. Some are running internally on our Amazon cloud. Others, we're using OpenAI's APIs for because it's just more convenient.
How does AI learn to deal with falsified data retractions, bias, et cetera, in studies? Thinking surge of retractions going on with data checking sleuths.
I might not be answering that question, but taking the term bias, I think this is one concern I have about large language models or models that are quote internet sized and are trained on internet sized data, is the sort of quality control aspect of the data. It's almost in some senses intractable because some people would say, oh, it's easy, just clean the data. But what does that mean? How do you decide on how to clean? There's actually a fantastic paper about this whole concept. It's got a long name, but it has the word stochastic parrots in its title. And they address this. They make the potentially controversial claim that it's impossible to do this. So, these models will always be, the generative models, not the kinds I showed, will always be plagued by some kind of bias, some kind of, harmful statistical associations. And actually, even the kind of classification models I've shown, they are also rife with bias issues. And that generally has to do with the data that are available and then careless use of models. Like a lot of data that are available are from resource-rich countries. So it's, healthcare data is mostly composed of white patients. And, that if those models are used carelessly, and they have been used carelessly in other settings, they don't do as well. Regarding the retractions point, I think that has to do more with, again, the irresponsible use of generative AI to, I guess, write papers that make fake makeup data. So I guess that's more of a Gen AI question, and I think that's more about being a responsible user of this technology.
I think you could imagine that these tools could be used for both creating fake information and for identifying fake information. Right? They're really under the control of the users, and then in terms of bias, right? Their biases are built off of human language. and how that language is represented online. Meta, for one, decided to not rescrape the whole internet, but to really try and create a cleaner data set that wasn't full of a bunch of like 4chan and, garbage. And they found they could train a better model faster with less data that way. So, some of the garbage data messes up how these things work. But if you want it to interact with humans, right, it's got to sort of have access to a whole range of human conversation. It's not an easy problem.
Just to add one more thing. I mean, I agree. I think it seems that companies have made so the problem that is not intractable, I think, is this kind of like high-level cleaning of the data to get rid of like racial slurs or things like that. But what is interesting is what we consider to be unbiased sources of information. It is kind of interesting, to sort of question that, because if you think of like Wikipedia, which everyone uses, it seems like pretty neutral. When you look at the demographics of people who contribute to Wikipedia articles, it's like 80% 20-something-year-old American males. And they can be as objective as they want, but whoever you are, your biases are going to come out, your inclinations are going to come out. And that's beautiful if all of us have an equal voice. But if it's just one, then that gets not just reproduced, but reinforced and amplified. And that's something that people are genuinely concerned about. I share that concern.
Yeah, I think it's a strong argument for more diversity in the training data and intentional work in that area. I had a discussion, somebody brought this up at work, and we were talking about this idea that, well, the model hallucinated something, but the model is outputting statistically probable things. And so it may not have an evidence, but it might be worth, like, it actually might be true. Like, these things are, able to make connections across more data than any human could ever read in 100 lifetimes. So, they know things, and people have shown in some studies, they know things that you can't easily elicit from them. That latent space that Akshay showed up there is full of information and connections and knowledge that people have not yet accessed.
Two great talks, really appreciate it. And I really appreciate the academic side and also the entrepreneur side. It's a similar question that I was just asked. How do you guys, from the academia and also from the business side, have ethical guardrails with what you guys do and don't do, and self-regulate what we can do? Because I think AI is out of the barn and moving quickly, and that's a fear and also an excitement.
That's a tough question. I think, even though we're a private business, we still adopted a lot of the same ethical frameworks that you would have in a university. So, when we're doing research, we have an external independent IRB. At the same time, like, there's commercial decisions that you make, within the bounds of what's legal, right? That, we talk about it internally as a management team. Are we willing to sell data for that purpose? But I think people who are dealing with this stuff need to be cognizant of the ethical angle, right? It's also legally complicated, right? There's now been some court cases of people, at least coming to agreements with attorneys general and things like that. So there's, people are watching what's happening now. I think, most people would be surprised just how much of their data is already out there. And it's already, like, that ship sailed a long time ago.
Just to really quickly add, so at Duke, they have, there's this, on the School of Medicine side, there's this big initiative to, this big responsible AI initiative. And it's led by Duke. The School of Medicine has a chief AI officer, Michael Pensina. He has a, great reputation for being, a very well-known biostatistician who really cares about these sorts of things. But more broadly speaking, reading about especially the things that have gone wrong, and also more about this area, has made me aware of the fact that, at least for like smaller cases, the proposed solutions aren't all that complicated. There are two concepts that were introduced I think they were both introduced by the same team. One is called data sheets and the other is called model cards. So it's a really simple idea. share, even if your data are proprietary, share a demographic breakdown of your data. What are the distributions? What are the salient points about your data that might make it immediately aware that it was all trained on just one type of person, or was all trained on just male and related information? And similarly with model cards, there's this other now famous paper called Gender Shades, and it was all about a testing of models that could do facial analysis. And these were models that were produced by IBM, Microsoft, and so on. And it was kind of when I think about it, it's sort of a silly task where, like, given a face, this model could predict if you were male or female. So it's very, artificially binary. And turns out this model did horrendously badly on Black women. And that's because the composition, again, it's the same story again and again. And so one thing that you can do is, instead of just reporting accuracy statistics in general, is to do it by demographic. And as a biologist, like I got my PhD doing animal research, and it's so convenient and common to do all of your research on male mice, just because it's easier, and people don't really think about that. And I see that now people are, the NIH is mandating that these should be balanced. So yeah, that was a sort of long-winded way of trying to address that.
So I really appreciated the talks. Thank you for that. The question that I have is for you, Mark, more specifically about how you de-risk the work that you're doing. For those of us who maybe use these models, Anthropic, whether it's Claude, ChatGPT, Perplexity, whatever it is, I find that there is often something wrong that needs to be adjusted. And when you're talking about medicine, and healthcare in particular, I know from the pandemic, we started this COVID Tech Task Force, and we were trying to just actually help people to know to get tested for COVID, right? And there is a inherent tension between the tech ecosystem and industry and medicine, where medicine really wants you to have 30 years of studies to, then make a decision to do something, right? To move to the next step. How are you de-risking the potential for your model, whether it's an in-house one or one that you're building on OpenAI's APIs, et cetera, to move forward? What are you doing to de-risk when it could be wrong?
Yeah. So we have certain IP that we've developed around this, but to give you the general framework of the way we think about this, if we're going to present information to a clinical user, we're going to present information that we have validated. And we took the approach, maybe that's pretty different than a lot of AI companies, that we were focused on FDA. So we thought about the outputs like a medical device. So we wanted to understand what the sensitivity and specificity was of each type of output that it could produce. And so that's been our general approach. And we've got, we've built some automation around that. We still use humans to validate samples of data, right, to make sure that the models are performing. We run tests on deployed models over time, right? So we look for drift or data set drift. It's not easy. That's why I say, keeping the stuff in production is hard, right? And, when you deploy at a different hospital, different health system, different patient population, doesn't work the same. Right, and things as simple as the way people type notes or what they call a heading, right? There's a lot of machinery under the hood that breaks up text to feed it to the machine. And if you break it up differently, right, it might break. So there's a lot of stuff that goes into this to make sure it keeps running.
A very short question. So if your AI recommends some cancer treatment and patient dies, who is liable?
So AI doesn't practice medicine. You as a patient can't go into ChatGPT and say, what should I do for my cancer? I think they've put guardrails to discourage it from answering those questions. We did a lot of testing on it early on, and it made up very convincing sounding stuff that was totally fabricated and didn't make clinical sense. But if you read it, you'd be like, man, it knows. So it's gotten a lot better. Those organizations are spending a lot of money acquiring medical data to improve that aspect of it. But in the end, right, it's a doctor who prescribes medication. So when we took ours to the FDA, the idea was this is information. It's explainable AI, so there's a regulatory schema at the FDA for it. And, a doctor can get information. Right now, and we did this when we were developing it. We talked to lots of oncologists. They use Google, right? They use WhatsApp to chat with their friends, right? There's a need for that information. People are filling it one way or another. And that argument resonated with the FDA because they use Google too. So the idea that, we can't regulate Google as a medical device because people are just searching, it's up to them to figure out the quality of the information. But it informs our thinking because we don't want people to believe things that are not true, right? Medicine is very hard too. There's a lot of contradictory information. When people are charting, they're thinking about the next physician. They're saying, this is what I think it might be, but it might be this. And, that's not very amenable to AI, right? Because it doesn't express uncertainty well when it's processing. So, it's a hard problem, but that's why we thought there was a lot of opportunity.
Great. Let's go ahead and take another question online. This will be our last question. Who should pay for the carbon dioxide emissions of generating AI for the user who runs equipment on solar? Can all AI run on solar? Nuclear power is too risky. Question for you both.
I mean, I don't know what the recent numbers are, but I mentioned this paper, again, I don't remember the entire title, but it has the word stochastic Paris in it. And actually, a lot of the very insightful questions that have come up tonight are addressed in that paper. It's now a little bit old, but I think one of the things they address is is this energy consumption justified? That's all to say. I have nothing else to add to that.
I mean, it's an interesting question. I think most of these big companies are looking for sustainable energy sources for this, in part because they're less expensive. Solar is less expensive now. As to, I think the market is kind of driving this, not individual people, or not so much.
So I'd like to go back to helping clinicians decide what to do in cancer therapy. There's been a history of scientific research trying to develop laboratory tests that would predict whether a person would respond to a certain type of drug or not. That went on for a long time. It got sort of to its peak with a test in which if you did this test and had enough tumor sample, you could predict with about 80 to 90% accuracy that a patient would respond. But even more, it was like 99% valid in predicting what a patient would not respond to, okay? Which is a pretty important piece of information. So that company got FDA approval for their test. It got accepted by Medicare, and the clinical community never adopted it. And so it went out of business. The company went out of business. So here you have a case, I'm arguing for biology, as you can see, where you're taking an actual individual patient sample, dropping an unmodified drug right on top of it and getting an output. And the question is, which is going to be more valuable? Now, AI may have a different way of looking at it, maybe through genetics or whatever, but that's just a point I'd like to have you discuss.
I have strong feelings about this. So when we were starting this company, we worked with a bunch of precision diagnostic companies. We still do. I've seen it. I'm a strong believer in precision oncology, that these tests, there are a bunch of them, they work in different ways, tend to improve the prediction of what might work. Oncologists sometimes believe them, sometimes they don't. We were trying in our tumor boards to elicit why. Like, why do they believe the Caris test for this patient and not that patient? And I think, there's a lot of subtlety to their thought process but I think for some of those test makers, the problem was just they didn't have a large enough study to convince doctors to prescribe it. And we still see that. Like, we still talk to diagnostic companies that are struggling with getting people to pay for their test, even though, like, in small samples, we've seen the data and, it often is predictive, especially what you say, like, it's a lot more predictive of what's not going to work. You know, there's more hoops to predict what works, but predicting, like, for cancer patients, don't waste time on things that aren't going to work. I think we saw that from, you know, hundreds of tumor boards. We've got data on 250,000 patients. You know, so we have some insights on the stuff that we believe are true that we've, you know, sometimes published. We got another publication coming out on this topic.
All right, we have one more question. Really, one more.
The world of AI is forever like drinking from a fire hose. There's always something new you have to learn. What has been the general advice that has helped you guys just stay at the forefront and allowed for you to just, because I've seen the articles. I know the Cornell's XI's publications, they always help out. But then is there anything that has allowed for you guys to just continuously just be able to learn and just keep up? Because sometimes it feels like you're drowning in the AI information.
I think for me, just being very curious about this stuff, I read about it a lot. I think the publication cycle for AI research is really different from other, like, medical research. People post on arXiv, and maybe they'll write a blog or Substack or something like that, and then they move on, right? And the people are doing, like, blogging to get people to notice their publications. We experience this, though. It's super hard to get peer review on these, and it takes forever because it's really difficult to explain. Like, it's hard to find anybody in the world who's got the time to go figure out, like, was your AI model legit? And, you know, I think there's a real peer review problem in this space. So, you know, often I think the cycle for us is read an interesting blog post, go look at the publication, and then start hacking away and seeing if we can replicate it and does it work, you know? And sometimes we move on, but, you know, you're sort of sifting, right? Nobody's sifting for you. I don't know.
I guess I have three answers to that. There's this saying that the best way to learn something is to attend a class on it. The second best way is to teach a class on it. And I teach a class on the intersection of AI and ethics with a colleague of mine in the law school. And that's really kept me on my toes. Second is I'm really, really interested in the intersection of broadly AI and biology research. So, you know, I have my favorite journals that I go to. Nature Machine Intelligence is a great journal. But as Mark said, a lot of this, not even necessarily like cutting edge, the next new LLM, whatever, is in arXiv. Mm-hmm. Like it happens really, really quickly. So that's a little bit of I guess it's like relying on algorithms or something that someone tweets or blue skies or like genuinely it's like it's following people who tirelessly share things that I'm interested in. I did have a third thing I wanted to say. I guess there are two ways to approach this. One is at a higher level where you can do a lot of really powerful things, as Mark said, through engaging with the API. You don't actually have to build these things from scratch or even fine-tune them necessarily. But I do believe that if you really want to get a good sense of how these things work, so this isn't really addressing your question, so it's not really keeping up with the newest and best, but just having a sense of how these things work, like it's becoming easier and easier to actually build these things from scratch. Like TensorFlow, Keras, PyTorch. I'm not saying they're trivial to use, but they've made building these things significantly easier than like 10 years ago. So that would be my advice. It's fun to play around with these things. And yeah, Hugging Face is a great resource.
I think it's fun. I know people in the government, the scariest thing for them is that, you know, it's like the 80s scenario of teenagers with nuclear bombs, that teenagers could do stuff with AI that, you know, would have huge ramifications, right? Right. But being curious and getting your hands on this stuff and using it is I think part of the way to learn and just staying curious, like coming to, you know, talks like this one. It's really, you know, this stuff can be fun and it's going to be really impactful.
Yeah, and you can restrict yourself to predicting blue and green circles. Like you don't have to do anything.
Yeah, or you know, you can just ask ChatGPT to tell you like that there's like a real problem here of information filtering that's going on like everywhere. All right, thank you.